SwayamPrabha. Digital India. Educated India.
Hello everyone. So, now we are using nonwoven for protecting from our noise pollution. So, this in this section last session what we have discussed that effect of nonwoven thickness on noise reduction. So, as the thickness increases the sound absorption coefficient also increases and also noise reduction coefficient. Then we have discussed a different layering process. So, 1 layer, 2 layer, 3 layer, 4 layers, 6 layers and 8 layers, but keeping the overall thickness constant, that we have discussed, and also for this different layer where we try to keep the areal density constant. So, different layer, and that effect of layering we have discussed in last session. So, with the increase in layering we have found that the stacking of different layers increase the sound absorption coefficient, that may be due to that cavity created and there multiple reflection or diffraction is there. So, that actually this reasons actually affect the sound absorption. So, when sound enters a cavity, it goes through multiple reflection and that decreases the sound energy, and rough surface, that is the scattering takes place, like here rough surface scattering takes place and which actually disturbance in the sound propagation takes place. So, that also helps in sound absorption. The repeated variations in the material density which results the viscous loss, like here the dense material and when there is no material in between the air cavity. So, this repeated change in the density of the material, like once it is in multi-layer, once it is coming from this fabric and then air cavity, again it is entering into the nonwoven fabric. So, that repeated change in the material which results the viscous loss, and this happens more in case of when there is a 8 layer. So, there is a 8 times changes in the material density. So, that affects the viscous loss. Now, we will be discussing the effect of compression on layered nonwoven assemblies. So, we have fabricated the system where the thickness can be changed in a controlled manner. So, it is not the compression tested, we have not put any compressive load here, because there thickness cannot be controlled, but what we have done with this system, we have controlled the thickness, like one screw system is there. By rotating the screw system, we can compress the nonwoven fabric to a certain extent, like total thickness, if we keep initial thickness 40 millimeter. So, 4 centimeter thickness, then if the pitch of the thread is 4 millimeters, that means for after one rotation, complete rotation, there will be 4 millimeter compression. So, effectively 10% compression will be there. So, by rotating this thread we can compress the material under controlled fashion. With the increase in compression level, the air layer between the nonwoven layers diminishes, because we have used the multi-layer, this multi-layer. So, when we are compressing the multi-layer, so the air layer is diminishing. Okay. And the phenomena of multiple reflection and viscous loss also diminishes, because there is a gap between the layers are reducing. What happened in the last study, which you have seen, that multiple reflection and viscous losses are there, that actually that reduces, thus reducing the sound absorption performance of multi-layer assembly. So, you can see here, when uncompressed, in uncompressed state the sound absorption coefficient is maximum or noise reduction coefficient is maximum, but when we compress like at 40% compression level, so this is actually minimum sound absorption coefficient. This actually that in the multi-layer, the air cavity in between layer, even within layer the pores also reduces, within layer air content also reduces. Now, what we have done after that, we have prepared a micro porous film. We have taken one film and we create pores, micro pores, okay, on the film, and addition of micro porous film with what we have observed increase the noise reduction coefficient. So, normal film and micro porous film, normal nonwoven. So, if you see the normal nonwoven is for, this is the S1, S1 and A1, we have used the same fabrics layers which we have used in our earlier study. S1 is a single nonwoven, one layer. So, two layers like that, and with the incorporation of micro perforated film and nonwoven. So, we have used the micro perforated film with the nonwoven, and what we found, the noise reduction coefficient increases. From this diagram it is clear the improvement is most significant at low to medium frequency range. So, at different frequency ranges, so from 63 hertz to 6300 hertz, what we have observed at low to medium range, you can see this range, the noise reduction coefficient is high, higher than the high frequency range, and between 100 to say 1250 at that range. So, noise reduction coefficient is high, and which maximum what is found is around 315 hertz. So, low to medium frequency range, it was observed that the noise reduction coefficient is high maximum by incorporating the micro perforated film along with the nonwoven. So, what happens if we, when we incorporate the micro perforated film, it creates a narrow air channel So, it creates narrow air channels between the that if it is there, and here narrow air channels will be there. So, nonwoven is there, after that narrow air channel will be there, which promotes the viscous boundary layer formation, and this leads to greater friction between the fiber or any solid material and air, and that frictional dissipation of acoustic energy will be more. The air layer between microperforated film and porous nonwoven allows thermal boundary layer to develop. So, when we use the microperforated film, this is the microperforated film and say nonwoven, this is nonwoven at the there, when it is sandwiched, then thin air layer is formed between the microperforated film and the nonwoven, and which allows the thermal boundary layer to develop, and combined viscous and thermal effect enhance the overall sound energy absorption. So, here first narrow channel creates the viscous layer. So, it is viscous effect will be there for due to the narrow channel, viscous boundary layer will be formed, and in between there is a air cavity that will results the thermal boundary. So, both combined enhances the combined ultimately affecting the more noise reduction coefficient. So, positioning of micro perforated film within the multi-layered structure and number of multi-layer microperforated film also affect the acoustic behavior. So, first we have seen that we have when we incorporate one microperforated film along with the nonwoven, it enhances the noise reduction coefficient, but positioning also affects significantly. Now, we can see here the positioning are of different types. This is N1 is only one microperforated film is placed. Here 8 layers of nonwoven is taken, only single layer of microperforated film. N2 we have kept 2 microperforated film. So, after 4th layer, so another at the top, one is at the top and another is at the after 4th layer. Then N4 there is a 4 layers, every after every 2 layers we are incorporating the microperforated film, and N8 that is alternatively we are putting after every nonwoven layer. So, this here number of microperforated films are increasing and it affects the this noise reduction coefficient. Now, incident sound is there. Now, if you see the this one N4, so in this way, so P1, P2, P3, P4 these are the perforated film, and when sound incidence is there, there will be viscous loss and thermal boundary will be created. Now, the resultant, so here what we have done here in this case we have placed single layer of my microperforated film P1 when we are keeping at the top, P2 single layer at the after one layer of nonwoven. Similarly, in this way we are placing the microperforated film. So, the result indicates the microperforated film shifts from frontmost at the top P1 to the backmost P1 to P8. P1 means when we are putting single microperforated layer at the top, and P8 means when we are putting the single microperforated film just above the bottom layer. So, 8th layer. So, that is the coding here. Now, if we see here, the peak absorption frequency moves towards the high frequency. Now, you can see here this is the P8. When we are shifting from P1 to P8, that at high frequency the sound absorption coefficient becomes higher, it is shifting, but at low frequency, a low to mid frequency, this is opposite case. So, it is a decreasing. If we position it from the top to the bottom, shifting the microperforated film, the characteristics of sound absorption coefficient changes with the frequency level. Now, as per one published literature, it consists of classical theory of microperforated panel. Here we have used a film, that this same, according to this theory, omega 0 m, that omega 0 is the angular resonance frequency, m is the mass reactance of microperforated panel here, but in our case it is a film, and this d here small d, d is the depth of the air cavity behind the microperforated film. So, air cavity will be there. So, behind the below the microperforated film there will be air cavity. So, the depth is d, and from there we can calculate, and c is the sound speed. So, if we want, so that is at different resonance frequency, this we can, these relations are there, and in our result we found that this result is, this relation is valid, and our present result actually follows this relationship. So, the angular resonance frequency is inversely related to the depth of the air cavity behind the microperforated panel in a nonlinear manner. As d decreases, omega 0, that is angular resonance frequency, will, that to satisfy the equation, hence the peak is shifting towards the higher frequency. So, when d decreases, so peak is shifting towards the higher frequency region. Thus, positioning of microperforated film in a multilayered configuration satisfy the equation. The frontmost microperforated film allows greater effective air cavity behind it, enhancing the sound absorption coefficient at low frequency. Whereas, at the back position it reduces the gravity because of the effective mass of the top layer. So, air cavity volume decreases, increases viscothermal damping, shifting the peak of absorption at the higher frequency. So, that for that we have seen that our experimental data follows the proposed theory. With the increase in number of microperforated film that we have experimented on, that N1, N2, N3, N4 and N8, N1 for single microperforated film and N8 is 8 microperforated film. So, with the increase in number of microperforated film within the layered nonwoven structure, what we have observed that as we increase the sound absorption coefficient reduces around the over all the ranges, okay, that we are getting the minimum sound absorption coefficient when we use the 8th layer, but at low frequency it is higher. We get higher sound absorption coefficient when we use the higher number of microperforated film. So, for that means for higher absorption at low frequency we can use more microperforated film, but when we are dealing with the higher frequency then we can reduce that number of microperforated film. As the resonance octave frequency reduces from 2000 to 6000, in this zone 2000 to 6300, the peak absorption also reduces from 0.97 to 0.85, 0.97 to 0.85. So, as the number of microperforated film increases, the absorption band becomes broad and the peak shifts towards the low frequency. So, this is a peak we are getting, we are shifting the peak towards the low frequency as we are increasing the number of microperforated film from 1 to 8. The maximum absorption also decreases with the increase in number of microperforated film, that is due to the higher reflection of sound associated with the presence of multiple microperforated film. So, here higher reflection will be there, that is why absorption is reducing. Although the multiple microperforated film widen the absorption band, yet the total acoustic energy absorption by nonwoven reduces. Now, we can get the relationship here. So, maximum absorption alpha max with respect to the number of layer, okay, of microperforated film, we get the linear relationship. So, from there we can if we know the number, if we need certain value of maximum sound absorption, then using this empirical relationship we can calculate the number of microperforated film required. Now, we will discuss the acoustics of rib knitted screens. So, this is actually in commercially it is very important that in the automotive silencer, in the exhaust which dominated by the glass fiber in the form of nonwoven, and the problem here is that due to the vibration at the exhaust, this glass fiber gets actually splitted, and that shredding takes place, and it glass fiber comes out, and exhaust with the exhaust it actually mixes with the environment. It comes to the small glass fiber dust, or small glass fiber comes into the exhaust. So, glass filled silencer blow the glass fiber dust out during the application, due to the vibration, which is mainly governed by the vibration and hot air flow in the silencer duct. So, there was a study which they have studied that retained weight. So, there is a standard material they have used where there is no loss, but when someone used the basalt wool mixed with the at 600 degree Celsius and basalt wool at 700 degree Celsius, it was found that there is a significant reduction in mass. That means, at higher temperature the reduction rate is very high. So, it can go up to say around 80% weight, that means around 20% loss in fiber which has been observed. So, that is due to the fiber dust or fiber small fiber particles coming out due to the vibration. So, it is a which increases the health issues by releasing the micro glass fiber dust in the air. Okay. And to minimize this glass loss from the glass nonwoven, we need a protective layer also. So, glass nonwoven is very commonly used for high temperature filtration and acoustics. So, for that if we sandwich the glass nonwoven, this is nonwoven, and if we sandwich the glass nonwoven in between the knitted fabric layer, then we can get say continuous protective layer made of continuous glass filament may reduce the this glass fiber release, glass fiber dust release. So, that was our basic objective. So, nonwoven is sandwiched between the knitted layer. A knitted fabric works as a both an upstream and downstream restrictive layer. So, that will restrict, and also in addition to that knitted fabric will enhance the sound absorption coefficient. So, in our study we have done both the dust release, fiber dust release characteristics, and also the sound absorption characteristics. The aim of this study is to deliver an understanding of various knitted nonwoven sandwich structure on acoustic absorption characteristics at in the harsh environment, okay, like at high temperature, high vibration, at a vibration level, which actually takes place during the automotive, at the automotive or industrial silencer or machine or duct housing. So, in all this application, most of the cases we use the glass fiber due to is cheap and high temperature resistivity. So, you can see the role of knitted structure. So, here is the porosity and straight pore. So, straight porosity we have measured. In this study, 3 parameters of rib knitted structures were considered, that is roving linear density, which is kept 20 to 200 to 600 x, knit stitch length 8 to 12 millimeter, and roving type flat textured. So, 2 different types of roving type also we have used. So, all these parameters were selected because they are directly affecting the pore characteristics of the material. So, here if we change the roving text, the pore keeping all other parameters constant, that will affect the pore structure, even stitch length. And roving type, flat roving will create the straight pore, and textured roving will create the tortuous pore. So, tortuous pore is important, as we have discussed earlier, that if we can create the tortuous pore, then the sound absorption will be high. That so, we have selected our experimental parameters. The trend suggested that knit made of textured roving are slightly more porous and have fewer straight pores. So, this will create the tortuous pore. The straight as well as overall porosity decreases with decreasing the stitch length, that we know that as we decrease the stitch length at lower stitch length, the porosity will be low, and also with the increase in roving linear density, keeping all other parameter constant, the fabric will be compact, the porosity will be low. The increased rigidity and rough surface of textured roving prevents internal sliding. So, that there is a this is a textured structure and flat filament. So, here in flat filament there is a chance of internal sliding between the threads, but in textured there will be locking, proper locking. So, internal sliding will be less and loop deformation will be reduced, thereby maintaining the integrity of the fiber loop junction. So, in case of textured, so we will get the stable loop structure. So, loop pores remain large, there will not be any shift. So, in contrast, flat roving knit loop junction becomes loosened due to relaxation, which causes the large open pores to split into multiple smaller pores, because the fibers get split. So, one large open pore is there. So, there in that case what it is there, that will be, it will be splitted and small multiple pores can be there, because these fibers are not locked. So, here we can see this is textured and this one is flat. In textured, the pore structures are almost uniform, but here we have got the splitting of the pores. Now, the sandwich fabrics were prepared, the nonwoven is at the middle, and in both the sides knit structures were created. Now, from here we can see the mean noise reduction coefficient increases with the texturing. So, flat to textured, if we increase that, if we textured when keeping all other parameters constant, the noise reduction coefficient increases, and also linear density at coarser linear density we get higher inertia, and also for smaller stitch length, lower stitch length we get higher inertia. So, if we use the textured yarn from the coarse roving with the lower stitch length, then we will get the maximum noise reduction coefficient. So, textured roving shows better sound absorption. With the increase in linear density, sound absorption increases. Okay. And here you can see between 200 to 400 tex, the rate of increase is higher as compared to from the 400 to 600 tex, and similar trend is there from although it is a negative sense, when we increase the stitch length, initially from 8 to 10 there is a higher reduction in noise reduction coefficient, and from 10 to 12 there will be further reduction. Now, let us see the type of pores. These are the straight pores made from the flat yarn, we will get maximum straight pores, and for textured filament, if we see, there will be mixture of straight pores covered by tortuous pores. Okay. And considering the knitted fabrics as a perforated plate, earlier we have used the perforated film. So, you can consider knitted fabric as perforated plate with cylindrical holes normal to the surface backed by nonwoven. The perforation radius directly affect the sound absorption of the sandwiched material. Lesser perforation radius and straight porosity. So, increase the acoustic impedance of the sandwiched material. A too small perforation radius and a straight pores will hinder the absorption as well. So, if there is a too small pores, as the losses in the viscosity boundary layer of the sandwiched pore will reduce. So, texturing enhance the sound absorption of the material by imparting the fibers in the straight pores. Okay, that in the straight pore we are imparting other fiber and making the pore tortuous. So, we are making the pores tortuous from the straight to tortuous pores, and that enhances the sound absorption coefficient in case of textured roving, and creating the perforation in the compactly bound fibers inside the roving. So, that in flat there is a compactly bound fibers, and when we texture there will be we are creating the pores. The presence of textured rovings produce fibers inside the straight pores, increasing the flow resistance of the knitted structure. So, that we have already discussed. So, presence of straight pores diminishes the sound absorption capability of the knitted fabric. This is a straight pores, the sound absorption capacity will be lower. So, here air flow rate also is showing the similar trend. So, that we have already discussed this. So, with the increase in stitch length, the average sound absorption coefficient reduces, and also with the increase in takes, the sound absorption coefficient increases. Now, we try to assess the vibration fiber loss. So, due to vibration there will be fiber loss. The vibration loss of fiber on in the nonwoven has been an issue worth addressing. So, as we have discussed, that is a very important issue. So, fiber loss between knitted, nonwoven, knitted sandwich structure was compared with the nonwoven alone. Now, for that we have developed one system, an instrument has been developed to assess the vibration loss. This is the instrument where this instrument is placed on a vibrating motor. The vibrating motor generates the required vibration by controlling the RPM, and then sample housing. This is a sample, we can place the sample, and whatever the dust generated during the vibration, it falls through the perforated plate on the back fiber collection paper. There will be paper there at the bottom, the fiber will get collected. So, fiber loss was measured at different level. This is the fiber loss. So, milligram per square meter per hour. So, these are the sandwich fabric, 15 millimeter nonwoven and 24 millimeter nonwoven. So, we have calculated the measured the this fiber loss. So, when there is a this sandwich fabric is there, and we found that fiber loss is very low, and without sandwich there is a fiber loss. This is only nonwoven fabrics are, this is nonwoven and nonwoven, and this is the sandwich fabric, and due to the presence of knitted structure, it prevents the fiber loss. Fiber loss reduces to a greater extent. Now, we can see the video of this system instrument. We can now this is running, and we can very well see that there is a fiber loss. The fibers are collected due to the vibration, and this glass fiber dust actually goes along with the exhaust, and ultimately it goes with the air. So, that is actually it is a very it is polluting the air. So, for that we found that if we sandwich the nonwoven with the knitted fabric, that gives better protection, and also the insulation characteristics increases, sound absorption characteristics. Now, you can see very well that these are the there is a dust. Now, acoustic characteristics of warp knitted screen. So, we have produced warp knitted structure. Okay. These are the warp knitted structure, and we have developed a different looping pattern. Now, this 15 different types of fabrics of were produced, polyester tricot structures were developed, and sound absorption, transmission and air resistivity were studied. Now, we can see the sample coding. So, group CBE coding. So, you can see this is looping diagram, and here are the microscopic image of the fabric. Now, if we see the coding is that is CBE coding. CBE means that is closed loop, B is the back guide bar pitch variation, and E is the equal lapping. CBC closed loop, back guide bar pitch varied, and C is counter lapping. Similarly, we have produced the CFE and OBE. CBE is actually grouped as T1 to T4, CBC T5 to T8, CFE T1 to T10, T1, this will be effectively T1 to T1, T9, T10, T11, and OBE is A1, A2, A3, A4. So, this are the basically coding. So, T1, T2, T3, T4. So, this is the CBE type of combination, that means closed loop, back guide bar pitch variation and equal lapping. So, from there we can see the A, B, C, D, these are the variations of the looping, and accordingly we can see the microscopic image where T4 that is D, this structure T4 with this structure, here we get the maximum covering. So, similarly, we have developed other structure. Here this is the lapping pattern CBC, this is the lapping pattern here. So, we get a T5, T6, T7, T8, then CBE, CFE. So, T1, T9, T10 and T11, and OBE, A1, A2, A3, A4. So, accordingly the lapping diagrams are there. So, then we have studied the sound absorption coefficient. So, sound absorption setup, the tricot is backed by 15 millimeter air cavity one. So, the fabric then 15 millimeter air cavity is created. Another case, the tricot screen is backed by 15 millimeter polyester nonwoven. Two sets we have produced. So, standard as per the standard ISO standard we have tested. This is the system. Here this is the impedance tube, and the fabric warp knit fabric is there, and here 15 millimeter air cavity and 15 millimeter hollow polyester nonwoven. So, these two experiments we have done. Now, sound transmission loss test setup is there. So, tricot screen only placed between the inlet and outlet. This ASTM standard. So, you can see here the sound transmission, earlier case it was sound absorption. So, sound absorption, the tricot is placed at the end, where at the back there is a 15 millimeter air and nonwoven respectively, and when we measure the tricot sound transmission characteristics, there the microphones are on the both sides. So, where we measure the sound energy before entering to the fabric and after entering, and there is a anechoic termination where sound will get absorbed, there will not be any reflection. So, air flow resistivity was tested by air permeability tester as per ISO 9000 air flow resistivity. Now, try to see here the trend. Air flow resistivity increases with rising underlap pitch. However, the rate of increase varies across the different fabrics. So, with the underlap pitch, if we increase, the air flow resistivity increases. Air backing and nonwoven backing. Here this is nonwoven backing. Here we have air backing system. So, if we compare with these two, both air backing and nonwoven backing configuration, the noise reduction behavior follows the similar increasing pattern with the increase in underlap pitch. The counter lapped structure shows higher energy compared to other structure. Here this is a counter lap. So, counter lap structure, that these structures distribute the yarn float in opposite direction, covering more space in between the consecutive wells. So, that is higher resistance will be there. This results enhance sound energy dissipation, as the structural complexity provides the point of reflection, absorption and scattering of sound. So, this pore structures are becoming complex when we use the counter lapped structure. The rise in noise reduction coefficient is exponential in open loop structure. If you see, that is open loop structure, it is exponential. It is open loop structure when we increase the that exponentially increases with the increase in underlap pitch. So, as the underlap pitch of the open loop structure increases, the inter yarn gaps reduces significantly, which results the greater noise reduction coefficient. This leads to improve in impedance matching between the air and the fabric and facilitating better sound absorption. The impedance matching will be there. Now, sound transmission loss, if we see the transmission loss behavior of the fabric across the various band, here T1 is having the lowest sound transmission loss and T4 is higher. So, to compare the transmission loss, all the structural parameters, the area under the transmission loss curve has also been evaluated. The noise reduction coefficient, NRC, and area under the transmission loss curve shows a similar trend to that of air flow resistivity. That is important. So, air flow resistivity and the noise reduction, that is noise reduction coefficient and transmission loss, okay, similar relationship is there. So, area under the transmission loss curve, noise reduction coefficient and the air flow resistivity, they have the similar trend. The sound absorption coefficient, you can see the similar trend with the airflow resistivity and also sound absorption, sound transmission loss. That means that there can be some relationship between all this. So, if we can assess the airflow resistivity, from there we can predict the sound absorption loss and sound transmission loss. So, TL transmission loss has direct relevance with the airflow resistivity and shows identical behavior with the underlap pitch. They are totally identical behavior. The frequency sound absorption loss curve. So, this is the frequency and sound absorption loss curve of all the tricot backed fabric with the 15 millimeter air layer and along and plotted with the 15 millimeter nonwoven layer. So, these are the 15 millimeter nonwoven layer and then 15 millimeter air layer. It is noticeable that the T4, T8, T11. So, T4, T8 and T11 shows higher sound absorption coefficient, okay, in all the frequency than that of the nonwoven itself. So, if we see the nonwoven, this is the red colored curve is of, this is for nonwoven. So, as compared to nonwoven, all these fabrics T4, T8, T11, they have the higher sound absorption coefficient. If we see the nonwoven has got higher GSM, higher aerial density than T4, T8, T11 and A4 also. They have much lower GSM, but still this knitted fabric, knitted structures are giving higher sound absorption coefficient. So, at lower thickness. So, we can, so that lower thickness and also at lower mass aerial density. So, we can use this knitted structure for specific purpose, particularly where the harsh environment is there, and we can use along with the nonwoven structure by sandwiching the fabric. And based on all our experience, what we have thought that we in this all these measurements were done without any vibration at normal temperature using normal that test is as per STM, and but there is a requirement of real life testing. In real life test, where we need the vibration, there will be a certain vibration and at high temperature will be there. So, that for that we have developed one instrument and we have studied in detail of different type of fabrics. So, that we will discuss in the next session. Till then, thank you.